Today we are going to study about Drude model of electrical conductivity. So this is explained this is purely a classical concept. So it means that the Newton's laws will be valid and we will not be talking about any quantum effects here. But in order to make a comparison of conductance with in quantum mechanical structures, in nanoparticles or nanomaterials, it is very important to understand this model first. So first of all, what is conductivity? We know very well that resistance is given by resistivity into length of a conductor divided by the cross-sectional area. So inverse of resistivity is known as conductivity. So and inverse of resistance is known as conductance. So conductivity can be written in terms of resistance, length and area, cross-sectional area of the conductor. So this Drude model of electrical conductivity is based upon the kinetic theory of gases. So it was assumed that the electrons in a conductor, they are moving in all the possible directions randomly, just like atoms or molecules in gas are moving. So they will be moving in all possible directions randomly, and therefore there will be no net motion of electron in any particular direction. And so there are some assumptions made in order to use a kinetic theory of gases to metals, which we will discuss. And so in the absence of electric field, the net motion is random in all possible directions, so there is no net motion in any particular direction. While in the presence of electric field, there will be some net motion, and therefore there will be some flow of current that will be taking place. So it is assumed that these electrons, they are moving in all possible directions and they collide with lattice imperfections, and when they are moving from one collision to the other, they are moving in a straight line. So this is one of the assumptions. And when they collide after the collision, they don't remember what was their direction or what was the velocity before the collision. So they start moving with the thermal velocity, which is provided by whatever temperature we are working at. So whatever temperature the conductor is at, so that will provide this thermal velocity to the electron. While it will not remember its direction, so it will start moving in any random direction. So the time between two collisions is actually given by tau. So it is the mean time between two collisions. So what you can do is you can just find out different times, like if this is T1, T2, T3, T4, and then just take an average of it. That will give you the mean time between collisions, which is also called the relaxation time. Yeah, so we have covered all the postulates. So when we are saying that there is no electric field and the electron is moving just because of the thermal energy, so then and also we know that this model is based upon kinetic theory of gases, so we can find out the total energy of the electron, which will be 3/2 kT, where k is the Boltzmann's constant, and from here we can get the thermal velocity, which will be 3 kT/m. So at time 0, if temperature is 0 Kelvin, then there will be no thermal velocity, but it means that all motion stops. But this is purely a classical concept, but quantum mechanically this is not true. And at some room temperature, let us say we are talking about 293 Kelvin, and if we can find out the velocity, it will be around. So this calculation we are doing just to get a number, an idea of the quantity actually, and not just a qualitative analysis. So if we know this temperature, we can find out the thermal velocity, which will be of the order of 10 to the power 5 meters per second. So although we have this large velocity here, but the average of the velocity will be 0 because there is no electric field, and the direction will be in all possible directions. So the net velocity will be 0. While in the presence of electric field, suppose that we are applying this electric field on an electron, so it will increase in velocity based upon the electric field. So by Newton's law, we can use F is equal to ma, and which this force is being provided by the electric field. Therefore ma will be m dv upon dt, because acceleration will be dv upon dt, which will be equal to qa. Now we can integrate it from some initial velocity to some intermediate velocity, from initial time to some intermediate time. So after integration, we get V is equal to QE upon ME into T. But if we use this relation, we'll see that if time will increase, then velocity will keep on increasing. But this is not true, because velocity cannot increase indefinitely. So it will get saturated, and it will have some constant value after some time, which is also discussed, and I have derived that also. That also we can derive. But here, just for concluding and understanding the concept, we see that it cannot increase unlimitedly. So this time has to be some constant number. So this actually, if we average this time, it comes out to be a constant number, and this average of the velocity will be drift velocity because of the electric field. So we are not considering the thermal energy here, so the velocity due to thermal energy here. So this average velocity will be called the drift velocity, and average time will be called the relaxation time, which will give you the mean time between collisions. So now this becomes a constant, charge is a constant, on the electron is a constant, electric field is a constant, mass is a constant. So we will get a constant value of the drift velocity, and this velocity in the presence of electric field is drift velocity. So this drift velocity is given by this relation, which depends upon relaxation time. But relaxation time itself actually is temperature dependent. So and this term here, it turns out to be equal to mobility of the electron. So mobility is given by E tau upon ME. So we see that the mobility depends upon the relaxation time, which means that if there will be larger mobility, so it means that electron travels a longer distance before colliding the lattice. So in order to get an idea of the drift velocity, we are just making some small calculation. Use tau to be this and electric field to be 1 volt per meter. We calculate drift velocity to be of the order of 10 to the power minus 3 meters per second, which we see is very small as compared to the velocity due to the thermal energy, which was of the order of 10 to the power 5 meters per second. So in actual, the velocity of the electron will be an addition of thermal velocity and a slower component, which is the drift velocity. Now in order to find current density, which is current per unit area, we see that it is given by QE and EVD. Now does it really actually, is it equal to current density, which is current per unit area? Let us just check dimensionally if it is true or not. So NE actually is the number of electrons per unit volume, drift velocity is distance per unit time, and charge is charge of the electron. So we can just keep Q as such, and NE will be number per unit volume, and dimensionally VD will be distance per unit time. So distance and volume can cancel, and we'll be left with area. So it will be charge per unit time per unit area. So charge per unit time will give you current. So it will be current per unit area. So dimensionally this term Q NE VD will turn out to be equal to current density. So we can replace now the drift velocity that we have calculated, and also we can also compare it with this equation, which is Ohm's law, which is J is equal to sigma E. Now let us try to understand the origin of this equation, how we get this J is equal to sigma E. So we know that R is equal to rho L upon A, which can be then in Ohm's law V is equal to IR. Put R here, and then rho is resistivity, which will be the reciprocal of conductivity, and L upon A. So V upon L is actually potential upon potential difference upon length. So we know that line integral of electric field is given by delta V, or potential difference. So from here we can, if we are integrated on length L, so we'll get EL is equal to V. So from here we can replace V upon L will be equal to electric field. So electric field will be current density divided by conductivity. So from there we can get current per unit area, or current density will be equal to conductivity into electric field. So from here we can use this relation, and we can compare these two equations, which is 1 and 2, and then we can find out this value of conductivity. and conductivity also contains mobility. So if the mobility of the charge carrier increases, conductivity will increase, because this term is actually mobility. So and if the number of charge carriers per unit volume will increase, the conductivity will increase. Okay, so in a semiconductor, because you know that we'll have mobility for an electron as well as an hole, so you can find out the mobility for an electron as well as a hole, and then putting it in the value of conductivity, because it will be q square into tau e Ne upon Me star, into where this Me star means the effective mass of the electron and effective mass of the hole for Mh star. So the total conductivity will be given by this relation. So this is just a small calculation that I have done.